All right. Let's see what happens here. First one, 2, 5, 8, 11, 14, 17. What does that add up to, Stephanie?
That adds up to 57.
57? Nope, that one's not even better. Oh, seriously. All right, second one, 4, 8, 16, 32, 64, 128. So what'd you get? Say again? 252. 3, 5, 9, 15, 23, 33, 45. Charlene, what'd you get?
133.
729, 243, 81, 27, 9, 3. Those are supposed to have negatives in front of them. But they didn't, so just add these up. That's fine. What did you get, Casey?
1092.
1092. Okay? And then 3, 7, 15, 31, 63, 127, 255. Kate, what'd you get? Sorry.
501. 503.
Say again?
503.
503. Like that?
Yeah, same. Okay, whichever.
Oh, I can't read my handwriting.
Yeah, 501.
Alright, everybody agree with those answers? Yes? Alright. Oh. So what you've just done here is you have just done a series. So a sequence is the list of the terms that make that up. A series is when you take all those terms and add them up. Okay? So we're still dealing with the list, but we're doing something different to it. We're not just looking at the list itself. We're interested in what the sum is. This is sometimes called the sum of a finite series. This can also be called partial sums. Seriously, what is going on with this these days? This is crazy. Okay, so if you see either of those two phrases in your directions, they basically mean the same thing. And it basically means you're going to take this list, which is finite because we don't have any indication that we're supposed to keep going from here. We've gone out a certain number of terms and then we've stopped. So we have a finite sequence and we are adding those numbers up so that we get the sum of a finite series. Okay, makes sense? Now, there's some notation that goes with this that uses the Greek letter sigma. The sigma is this one that kind of looks like a funky E. And the sigma in mathematics almost always represents a sum. Okay? So when we are saying that we want to take the 2 plus the 5 plus the 8 plus the 11 plus the 14 plus the 17 in that first sequence to get the 57 as an answer, one way of writing that is to say I want to take the sum, so use your sigma sign, of whatever the function for a sub n is. So remember we did those last class, coming up with those functions that represented what the equation would be. What the sequence would be. One form of the function is this. 2 plus 3 times n minus 1, which if you simplify it, ends up being 3n minus 1, which is what we came up with last class. Okay? So we're saying I want the sum of this 3n minus 1 function that we came up with for the sequence that we're trying to add up. And then because it's finite, we have to indicate with the sigma sign which terms we want to add up. So on the bottom, underneath your sigma sign, you always say what term you want to start with. Usually that's going to be a 0 or a 1. And then at the top of the sigma sign, you indicate how many of the terms you want to add. So this is saying I want to add all of the terms, the a sub n's, from n equals 1 up to n equals 6, which means I'm adding the 1, 2, 3, 4, 5, 6 terms, the first 6 terms together. And because we're now looking at this function, then that means if I put 1 in for n and worked it out, I would get this 2. If I put 2 in for n and worked it out, I'd get that 5. And I put in all of the integers up until I get to 6, and that's what I'm going to add up. So this is a more algebraic way of representing what it is we're doing here when we just had the list and we added up all the terms. And again, this works for a finite series or for partial sums because of the fact that we are limiting the terms. We are saying there's a certain place we're going to stop, and that's what we're going to add up. And so this works in those cases because we have a starting term and an ending term that we can indicate here on the top and the bottom of our sigma sign. Any questions about that? Does that make sense? So back to a little bit of vocabulary here. If we are talking about an infinite sequence, so something that keeps going on and on and on and on and on, then the sum of the first n terms of that sequence would be called finite. Again, we're taking a limited number of terms, we've got a starting place and we have a stopping place, and we're adding up everything in between. So they're showing that we're actually stopping here at whatever a sub n is going to be, and we write that, this time they're using I as the subscript, so we've got the sigma I equals 1 up to the n of whatever a sub I is. That's just a very general way of representing what we're trying to accomplish. Okay, that's what we were just talking about. But then there are cases where we can actually take the sum of the terms of an infinite sequence. Now that may seem a little strange, because if it keeps going on and on and on and on and on, how can we possibly ever get the sum of it? Well, we're going to find that there's only certain types of infinite series that we can do. But it is possible. So, if we have an infinite series, then that's going to be denoted basically in the same way as our finite series was, but instead of some n value up here that tells us where to stop, we're going to have an infinity sign up there that tells us that we're not going to stop. So we're going to keep going and going and going and going and going. Everything else about the notation is the same. It's still a sigma sign. It's still usually 1 or 0 at the bottom because that's where you're going to start. We're still going to do that with whatever our function is, which is what a sub I represents. It's just that instead of having an actual number on top, we're going to have infinity on top. Question?
Wait, what is, I can't read the
So this one's going from I equals 1 up to n,
Okay.
and this one's going from I equals 1 up to infinity.
Oh,
And both of them are doing that for a sub I.
okay, thank you.
This is also in your book, so if you're not quite getting it down, you can get it tonight when you look at your book. Okay? So most of the time we deal with finite series, but there are going to be examples that we're going to see that we can do with infinite series, and that's really going to come up more in our next couple of lessons. When we start talking about some specific types of sequences and series, that's where we're going to see how it's actually possible to get the sum of an infinite sequence. Some properties that you can use if you're actually trying to come up with what that sum is, and you have this kind of notation using the sigmas, there are some shortcuts you can use to help you out that might help you evaluate and get your answer. For example, if that's your notation, where C represents a constant, so it would be like someone saying, I want to take the sum from I equals 1 up to 5 of the number 3. Okay, so what does that mean? It means that every term in your sequence was a 3. So if you want the first 5 terms, it's really just taking your constant times whatever your number up here is. That's going to be your answer. Okay, I'm just going to take 3 times 5, and 15 will be my series answer. So that's what this one is saying. If you have a summation of a constant, what that's technically saying is every term in your sequence was that same number. And so in order to get the series answer, you're just going to take however many of those terms you wanted times that constant, and that's going to be your answer. Okay? This one is saying that if we have some constant C out in front of our a sub I, then it is allowed to bring that constant out in front. So an example of that might look like this. I want to take the sum of I equals 1 up to 4. And maybe I have an equation, a function that looks like 3 I plus 3.
4.
Yes. Let me change color here so it doesn't blend in so much. There you go. So you could rewrite this as 3 times I plus 1. So, my brain's just not working today. Sorry, guys. Still on sick day mode. There we go. 3. There we go. So we have this constant 3 that we could maybe pull out of that function. And because it's now a constant out in front of that expression, we could even go one more step and say, well, instead of having to multiply 3 by this thing all of these times, I could just take 3 out in front, figure out what the sum of all of the terms of I plus 1 are, and then take that answer times 3, and I'll get the same answer. That's what that property's saying. So if you have some constant that's out in front of an expression, it is legal to pull that constant out in front of the sigma, do the summation with just the simplified function, and then take the answer you get from that summation times the constant last, rather than taking it times every time. And it'll get you the same answer. Okay, property number 3 says that if you are, for some reason you end up taking the sum from I equals 1 up to, let's say, 6, and for whatever reason, you end up with 2 different functions that you're trying to work with. So maybe you've got a 3i plus 1, but then you're also adding 2i to that. Now this is a fairly simple example, so obviously you could just take the 2i plus the 3i and simplify your expression. But maybe it's not quite that simple to combine them. What this one is saying is it is totally legal to split this up and take the summation of your first one plus the summation of your second one separately. Okay, so maybe you have something that doesn't combine very well. Maybe you have 3i plus 1 and then you have like a log of I. I don't know, I'm just making stuff up here for example's sake. But because those two things would not actually combine to simplify, what this is saying is go ahead and take the summation of that first part, get that answer, take the summation of the second part, get that answer, and then just add those two answers together. And that will work the same. You'll get the same answer that way. So that might help make things a little easier if you're trying to get an answer. And it works the same with subtraction. So whether you're adding two functions together or subtracting two functions from each other, you can split it up and take the summation of each one separately and then add or subtract the answers you get, the sums you get, rather than trying to do it all at once. Okay, so just a few properties or tricks to help you when you're trying to solve these out that might make the calculation a little bit easier. Okay, keep them in mind. So, if you are being shown a particular sequence that you're being asked to write the notation for it for a series, we want to try to use that sigma notation. So just those two that are boxed, I want you to try to rewrite that using that sigma notation. And again, this will be based on using the functions that we saw last class. So you can flip back and see what we came up with for functions for these, and then try to use that using the sigma notation.
Nobody posted that. Yeah. Find my friend, which is like a stuff. Yeah, that's the thing. Like you can put in like other friends' Apple ID, then you can like you can give them permission to track. It's just Apple to Apple. Yeah, Apple to Apple. So weird.
All right, let's take a look at this. So for the first one, we start out with a sequence of 4, 8, 16, 32, 64, 128. From last class, what did we say the function for that was?
2 to the power of n plus 1.
2 to the power of n plus 1. Okay, so for the sequence, the listing of the terms, that's how we're going to get the terms. But for the series, we want to add those terms together. So sigma is going to go out in front. What's the variable that's being used in my function? N. Which term are we starting with? The first one. And how many terms are we adding up? 1, 2, 3, 4, 5, 6. So that's the sigma notation that represents the same thing as what we have written out. Okay? And technically, what that represents is this. Right? Adding up those 6 terms, that's the sigma notation that represents the same thing. Okay? Same thing with this one, 3, 5, 9, 15, 23, 33, 45. What was the function we came up with yesterday for that? Or Tuesday? What was it?
3 plus n times in parentheses n minus 1.
Okay, so that's the function that gives us the individual terms. We want to add them up, so we put sigma out in front. What variable is being used in the function? N. Which term are we going to start with? And how many terms are we adding? 7 this time. So that is the sigma notation that represents this. Okay, and just to double check. Now, is this different than this? Not really. If we were to simplify to some extent, and I'm not talking about taking the 4 times 2 first and making it 8 to the n minus 1, because that's not right. But if we were to put in n values from 1 to 6, using that 4 times 2 to the n minus 1 power, we would get the same answers. So we talked about this last class, the fact that there's oftentimes more than one way to come up with what the pattern is, or more than one way to come up with what the function might be to represent that pattern. That's the case here. The 4 times 2 to the n minus 1 power is just another way of representing the same thing that's going on. Now, the reason it is this way, and we're going to see this more in our next 2 lessons when we get into specific types of lessons, is because this is one of those specific types, and there is a particular form to the function that always works with that type. And so the 4 times 2 to the n minus 1 is using that form of the function. But you don't quite know what that form is yet, so you don't necessarily think of it in that way yet. Okay? But it will give us the same answers as our 2 to the n plus 1. So either way would be okay. Okay, our second one though, we've got the same function as what it says we should have. We're going from 1 to 7, so that's all good. Okay, so if you are given a brand new sequence that you're supposed to write sigma notation for the finite series of, the first thing you have to do is decide what should the function be that represents what's going on in the sequence. You have to think of it as a sequence first. You have to think about what's the function going to be that's going to give me these different terms in this sequence. Once you've established that function, then put the sigma in front of it and set up your numbers to go from probably n equals 1 at this point up to however many terms it is that you're trying to add together. And then you have the notation for a series, which will add it all up. Make sense? So even tonight, I'm not sure that this actually happens, but just as kind of a tip on homework or maybe quizzes or tests, if you're being asked to write sigma notation for a sequence, look to see if that sequence was maybe already asked in a previous question about what would the function be. Because if you've already got the function from a previous question, then you can just use that for your sigma notation. Okay, so always kind of just check that out. See if this is a sequence you've already used, see if it's a sequence you've already written a function for, and if it is, then sigma notation's easy. If it's not, then you got to come up with the function first. Okay? All right, let's turn it around. I'm going to give you the sigma notation, and you need to come up with the sum. Go ahead and try all three of those. Let's see what you get for an answer. Yeah, so they're all starting with ones. First one goes up to 5, second one goes up to 6, and the third one goes up to 10. I guess you can't see that very well.
So if this equals 1, just plug in 1.
So we're gonna do all day Saturday since we're both gone.
I got 2, 5, 18, 11. So 3 times 5 is like, oh, that's
6 weeks out. So they're like 8, you're like 9. I do both of those.
I know.
I think you're It's 9 weeks. They don't break it. We got like 14. just switch us. We got a 2-hour bus ride each way. And Morgan and I went to sleep for the week back. For this.
Yeah. Wait.
I thought you were going down.
Yeah, we are 2-hour bus rides each way. What? Going to what? Is that what it is?
2 to the power.
This Saturday? And yeah. No, I'm going.
Because 1, 2, 3.
Justice, those concerns, Ebola. I don't know. And then there's a bunch of couple of fairs.
No.
Isn't
IVs start at 1.
Isn't it quiz bowl or?
So you plug in.
Because we're sharing a
So the first sequence.
Oh yeah, no,
This first 6 slot because
wait,
the other 6.
Yeah,
you
Jen,
want
that's
to start
what
by
it was.
using 1.
Who's in here?
You do 2 to the power of 1.
no, that was so
And then you go out 2 to the power of 2.
Wow. Okay. Basically, I'm seeing people places. We're doing this cool. Sujo.
Got him?
Got it.
All right, attention back up here, please. So for this one, tell me what my terms are that I'm adding together. Oops, get a pen on here.
2.
Bahar, what are my terms going to be?
8,
I'm sorry, say again.
2,
2,
5, 8, 11, 14.
okay. And then what's that going to give us when we add those all up?
40.
Everybody agree? Okay, so that's what you're doing. You're just putting 1 in, get the answer. 2 in, get the answer. 3 in, get the answer. 4 in, get the answer. 5 in, get the answer. And then add all the answers up. That's all it is. Okay? How about this one? What are my terms going to be? Hagen?
2, 4, 8, 16,
16 what?
32.
And what does that give me when I add them all up? 126. Okay, everybody agree with that? Did we get enough terms in? And we get 126 for an answer? Everybody agrees? Okay. How about this one?
0.
Because what are our terms?
5 and negative
5 plus negative 5 plus 5 plus negative 5. So the fact that I'm going 10 times, every 2,
It does start with negative.
yeah, sorry.
But it doesn't matter anyway.
It doesn't matter. Just like.
Yeah, so we start with negative 5, 5, negative 5, 5, and it would go 10 times, but you can see that every 2 are going to cancel each other out. So the fact that I go an even number of times means that in the end, it's all going to cancel each other out, and I'm going to get 0. But what if this had asked you to go 7 times?
It would be -5.
Then you would get negative 5 because every 2 would cancel, but then you'd have an extra negative 5 left that didn't get canceled with some other 5. Okay, so you'd have to make sure that you understood, well, it's even, every 2 cancel out, okay, I get 0. And if you can see a pattern like that, you don't necessarily have to write out all 10 terms. You just know that because it's 10 and it's even, everything will cancel out. I'm going to end up with 0 in the end. So again, sequences and series are all about patterns, and even in terms of getting your answer sometimes, if you can see that there's a certain pattern that helps you to get your answer, use it. What you cannot do is just put this into your calculator and say, oh, there's the answer, and not show me how you're getting it. You can check yourself in your calculator, but you can't just do it in your calculator.
This is one of those cases where infinity would work.
Where what?
Where infinity would work instead of 10.
Not quite, because by going out to infinity, you don't really know if you're supposed to end up at 0 or at the -5. Okay. One thing I do want to show you, because I think it's on here, but I'll be honest, I didn't look this up ahead of time, so I'm kind of flying blind here, but I think I remember how to do this. There is a way of doing these sigma things on your calculator, I believe. Anybody figured it out?
Is it in the book?
Sometimes.
Is what?
All the symbol.
In the book?
Sometimes
Is
you
it in
get
the book thing?
Maybe.
Yeah.
they work.
Oh, I see it. It's right there.
In the book? Is that where you found it?
Second tab.
Dude, it's strong.
Sorry?
It's in the second.
It's like.
It's in the second tab of the book.
The second tab of the book. So if we go to the book, nope, that's not the book. Try that again. Go to the book. Oh, look, it even says sigma. Couldn't make it more obvious, could they? So now which one of these do we want? Any ideas?
List.
Algebra.
Calculus.
Math. Nope. It's not math.
Oh, some of elements.
Could be calculus.
Never mind.
Sum of elements? Did you find sum of elements?
Yeah, but it's not. It doesn't have the sign. Oh,
It's just like.
it's just like a song.
Was it in list?
I think it might be a complex one.
Where is it?
Isn't it in a different section anyway? Oh, I found it.
Cumulative sum list. That looks.
Elijah found it.
Where'd you find it, Elijah?
Well, there's a sigma sign in operation.
Yeah.
So in the book still?
It's the one next to the book.
In the book. And do I want the second tab or do I want something else?
Yeah, the second tab.
Second tab, and I want
Oh, it's
operations.
Down.
It's pretty far down.
Math operators. Oops.
Oh, and
That's
then
not what I
you
wanted.
Find the sigma sign, and it
Math operators.
takes 4 parameters.
Sigma, 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 sigma. Whoa, there she is.
Parameters.
Yeah,
Kitty's like math. They're called my
By the way, we got a 20 out of 20 on this thing.
All right.
Did you show me?
Yeah.
Getting me on here.
Miss Gordon.
Yeah.
You can find it in the symbol next to the book. It's easier to.
Symbol next to the book.
And then there's a sigma right there.
Sigma.
There.
Here. Whoa, there we go.
Whoa! That was so cheap. Where is it?
So,
How are you okay with it?
moral of the story is, yes, you can find just about anything in the book, but it's kind of like looking in the dictionary for a word, right? And it's probably even a little harder because it's not necessarily alphabetical all the time. Okay, so if you can play around with some of the other buttons and find it there, that's easier. And because pushing that already sets up the form for us, it's really easy to put it in, right? We can put in our function. Let's see, what was one of the functions we had? Let's say our 3k minus 1. So I can go 3k minus 1 for my function. Since I'm using k, then that means k is going to go in there, and I want to start with 1. I want to go up to how many? 5 on that one. And once I have everything in, hit the return. So you can use this to check your answer to see that you're on the right track. But in terms of what you need to show me on a quiz or a test, I want to see your individual terms written out. Or what we're going to see with lesson 2 and lesson 3 is that there's certain formulas you can use to help you find the answer. I would want to see that work. So either individual terms or the formulas we're going to talk about, I want to see that work. I don't just want you to go, oh, equals 40. and not give me any indication of how you got that. Okay? Check it on your calculator, fine. But show me some work on how you got it. Because those kinds of questions will most likely be on non-calculator sections of a quiz or test anyway. Okay? So did everybody catch that? It's this button where we got our systems, right? But now it's second row, kind of in the middle there. That's where our sigma sign is. And then it just sets up the framework. You just fill in what you need to, and it'll give you your answer. Okay? Any questions on any of this with series? So series is not necessarily a complicated concept in terms of we have to explain it a lot, because we already know what a sequence is. But it was one of those things where if I tried to do it on Tuesday with the sequences, we wouldn't have gotten through it all. Okay, so that's why we kind of split that up. So once you know what a sequence is, then it's just a matter of adding those terms up. That's when you call it a series. Okay, so that's really all I need to. I'm not going to do that just yet. That's all we need to go through for this lesson. So you're going to have the rest of the time to work on homework. But for homework, I don't have the day 2 set up on Canvas yet, so I'm going to show you what the homework is from last year's course real quick so you can get it written down, and then I'll get it set up on Canvas for you. Being out yesterday, I got a little bit behind on that stuff, so that's actually not what I want. This is what I want. Pre-calc. Chapter 9, day 2. All right, so pages 613 to 615, we're looking at 67 to 73 odd. Yeah, okay, 67 to 73 odd, and then 79 to 91 odd. So it's 11 problems total.